In Chapter 16, Section 3, we're going to look at more problems involving line integrals. So let's take a look. In the first problem, it says, table of values of a function f with a continuous gradient is given. Find the line integral of the gradient of f dotted with a differential portion of a vector, parametric vector, where c has the parametric equations below. So we have x equals t squared plus 1 and y equals t5 plus t. So the parametric vector r as a function of t is going to be t squared plus 1 in the I direction plus t to the 5th plus t in the j direction, and that's for t between 0 and 1. So what we have to do is we have to take f as a function of r and dot it with the derivative of this position vector. So we have to say r prime of t is equal to 2t in the I direction plus 5t to the 4th plus 1 in the j direction. So just a standard derivative. And then we're going to say that the integral, the line integral across the gradient of f dotted with dr would have to equal f evaluated at the position vector evaluated at 1 minus f evaluated at the position vector of 0. And I got those numbers from these upper and lower limits on t. But if we plug those numbers into the position vector, we're going to get f of, when we plug in 1 into r, we're going to get 2 in the I and 2 in the j. So I'm replacing this t with 1 and then these two t's with 1. And you'll see that we'll get 2, 2. If we replace those two t's with 0, so we change this to 0 now, we're gonna get 1 in the I and 0 in the j. Okay, now why did we take this derivative? We took this derivative to see that this thing is not equal to 0. So r prime of t is not equal to 0. And therefore, c, the curve, should be continuous and differentiable. So I might have misspoke earlier. We don't actually plug in r prime into f. We're using the original position vector into f. Okay, but we don't know what f is. They never gave us the function. But we have a table of the values. So when x is 2 and y is 2, we would go to x is 2, y is 2 in this table, and the answer would be 6. So we're going to get this whole thing is 6 minus, when x is 1, let's use a different color here, x is 1 and y is 0, we get 3. So the whole thing is going to be, the line integral is just going to reduce to 3, which we have there. So first problem, not too bad. Take the derivative, see if it's not 0. If it's not, then that's good. It means the function is continuous and differentiable, and then we can plug in the endpoints of t into the position vector, get an x and y value that we'll then look up in the table, and we'll get a simple subtraction and solve for that line integral for problem 1. Okay, for problems 2 and 3, they're the same. So they're asking is determine whether or not F is a conservative vector field. Okay, so F of xy is a conservative vector field, if the partial derivative of F of xy with respect to y of the, how do I want to write this? The partial derivative of F of xy's I component with respect to y minus the partial derivative of F's j component with respect to x equals 0. Or the partial derivative of the vector field in the I component with respect to y equals the partial derivative of f in the f's j component with respect to x are equal. So this is interesting. We're not used to taking the partial derivative of an x component with respect to y. So it feels a bit reversed here. So we're going to test that on these two problems. So if we look, we're going to take the partial derivative of the I component. So it's going to be the partial derivative of e to the x cosine y with respect to y. Now if I take the partial derivative of that equation with respect to y, it would be e to the x times negative sine of y. Okay, then we're going to take the partial derivative of the j component, so of ex sine y with respect to x. Now the derivative with respect to x of ex is ex, and then we would just have sine as a constant, so it's times sine y. Now these are really close, but they are not equal. So this one with the minus sign would be minus ex sine y, and this one was positive ex sine y, and those are not equal. So they're close but not exactly the same. So because they're not equal, f is not conservative, is not a conservative field, and so we're not going to be able to calculate the function f of xy. Now we will do some problems later where we will do that, so we'll see how that works. But for now, we'll just say f of xy, there is no common function for this vector field, so we'll say does not exist. Okay, and that's problem 2. Okay, now let's try this, let's test this for problem 3, because it's pretty similar. So we're going to take, now we have 3x squared minus 4y, so we're going to take the partial derivative of 3x squared minus 4y squared with respect to y. So again, we take the I component with respect to y. And this is going to equal, so x is a constant, so it goes away. So this is just going to be minus 8y. Then we're going to take the partial derivative of 8xy plus 5 with respect to x, and we're going to get 8y. So the 8x, the x would go away, the 5 would go away, and we have minus 8 and 8y. And again, these are not equal. Close, but not equal. If they're not equal, then f of xy does not exist. And f is not a conservative vector field. Okay, so that's 2 and 3, very similar. Okay, 4, we're going to start off with the same analysis. So we're going to start with the I component. and we're going to take the partial derivative of that I component with respect to y, and we're going to get derivative of y would just go away, so it's ex, and then this is going to be plus cosine y. Derivative of sine y is cosine y. Then we're going to take the partial derivative of the second component, ex plus x cosine y, with respect to x. Derivative of ex is ex. Derivative of x cosine y would be considered just a constant, so the x would just go away, so we would be left with cosine y. And we see that these two are equal. They are equal. And so we would say f of xy is a conservative vector field. Okay, now what does that mean? Well, what that means is we can come up with some function that when we take the partial derivatives of it, we will get these values here. So, or we'll get the original components I and j. So basically we're going to say this. The partial derivative with respect to x, which we'll call f sub x, should equal, after we take it, y e to the x plus sine y. It's the I component of the vector field. And so now this is where we're matching x with I, the I component. And so we would say this implies that f of xy, notice no partial derivative, so no little x here, would be equal to, basically it's an antiderivative of this equation with respect to x. So we would say that this would be y e to the x, so the antiderivative of ex is ex, and if there's a y in front, it just stays there. But here's where it's going to change. Plus, if I'm doing this with respect to x, sine y is a constant. So the antiderivative of sine y with respect to x would be x sine y. So we just put an x in front of it. Plus, there could have been some function we'll call g that had y's in it. Because if I take a partial derivative of f with respect to x, any function that only has y's in it will completely go away. It will become 0. So there could have been an entire function, which we call g of y, that could have existed in this f of xy, such that if I take a partial derivative with respect to x, it goes away. So we're going to put that, it's kind of like a constant of integration if we do an indefinite integral. Similarly, we're going to say fy of xy would equal the j component of the vector field f, so it's ex plus x cosine y, and that implies that the original function f of xy would equal the antiderivative of ex with respect to y would be yex. So the only way we could have had an ex left over after taking a partial derivative is if there was a y attached to that ex, such that if I take the partial derivative right now, that y would go away and I'd be back to ex on the left. Plus, if I have x cosine y, the antiderivative of cosine is sine, so that original function must have been sine y. And then we would have plus, there could have been some function with respect to x in this original function. Now we look at it and say, this matches this matches this, and therefore I don't need these extra functions, gy and gx. You only need those if these two are different in some way, and you can say, oh, well, I can account for this by calling this gy, or I can account for this extra term by calling it gx. So because these match perfectly, I don't need these extra terms. We can chuck those out. And we're going to say pretty confidently that the original function is y(ex) plus x sine y. And if you take the partial derivative of that function with respect to x, you will get the I term on the vector field. If you take the partial derivative of that with respect to y, you will get the j term of the vector field. And that's, I guess, all we have to type there. So that would be the function we were looking for problem 4. Okay, very similarly, problem 5 is going to have a picture. We've got a vector field and we have two different curves, actually 3 different curves, and they all have the same starting point and they all have the same ending point. And we're going to see what does that mean. So they all start at this point, which is 1, 2, and they all terminate at this point, which is 3, 2. And they give us that the vector field is, in shorthand notation, no i's and j's, 2xy, x squared. So just like before, we're going to start by finding if this vector field is conservative. So we're going to take the partial derivative of 2xy with respect to y, and that would be just 2x. Then we're going to take the partial derivative of x squared, the j component, with respect to x, and that's also 2x. Now these are the same, therefore f is conservative. And so now we will do our analysis. We'll say if f of x equals 2xy, then that implies that f of xy is the antiderivative of 2xy with respect to x, which would be x squared y plus some possible function that only had y's in it. And the partial derivative with respect to y of that function should have simplified to x squared, which implies that the original function had to be x squared with a y on it, plus some gx. So if after I take a derivative, I'm left with x squared, that means there must have been a y on it, because the derivative of y in this context would go away. And just like before, we notice this is exactly the same as that, which means I don't need any extra terms. We can essentially say they're constants or they went to 0. And so we can say our function is equal to x squared y. And therefore, the line integral of the vector field xy dotted with dr is going to be equal to f at the second point. So at the, let me write this at the terminal point. Minus f of the starting point. Well, we're going to get that is the same. The terminal point is 3, 2. That's where all 3 curves terminate. Minus the starting point of all 3 curves is 1, 2. And we just have to plug those into, we have to plug x and y into this function here. So we're going to get, this is 3 squared times 2 minus, now plug this x and y into the same curve, and it's going to be 1 squared times 2. So this is 9 times 2 minus 1 times 2. This is 18 minus 2, which is 16. And because we proved this is conservative, all 3 curves have the same initial and terminal points. And another thing that we'll learn is, if we're talking about this in terms of energy or work done, it will take the same amount of work to go along this top curve or to go along this wavy curve, or to go along the bottom curve. So that's what it means to be a conservative vector field, is that the path you go from one point to another should not matter. You should get the same value, in this case 16 units of energy or whatever you want to consider it, to go from those 2 points. Okay, so that comes up and is useful, especially like in physics when you study particle motion and things like that. Okay, so that's problem 5. Okay, problem 6, pretty much the same approach. We're going to have the partial of, let's see here, the x term is 2x ey, so it's 2x e to the minus y with respect to y would equal minus 2x e to the minus y. So the partial derivative of e to the minus y, you just bring the minus down and then you keep it the same. And then we look at the y component, which is the partial derivative of 2y minus x squared e to the minus y, and this time is with respect to x. And if we do this, the 2y in front goes completely away. This x squared would become minus 2x, and then e to the minus y would stay the same. And once again, we see that these two things are the same. They are equal. Therefore, f is conservative, a conservative vector field. And then we can proceed to find that common function. So we would say f of x of xy, partial derivative f with respect to x, would have equaled this original I term, 2x e to the minus y, which implies that this function, taking antiderivative of this, an integral with respect to x, this should have been x squared e to the minus y plus potentially some other function that's only in terms of y. Partial derivative of f with respect to y should equal the second term, 2y minus x squared e to the minus y, implies that the function fxy should equal y squared minus, this one's a little tricky, it's actually going to be plus, because the antiderivative of e to the minus y would be minus e to the minus y, but there's already minus there, so there's a double negative, x squared e to the minus y, plus potentially some function that has only x's in it. And what we notice is that these two functions are very similar, except for, let's see if I can underline this. So this is exactly the same as this, so I can make these the same if I add this up here. So if I say this g of y was y squared, notice the partial derivative with respect to x, that would go to 0, so it does not change my I component of the vector field. But if I add that, now they are exactly the same. So our function f of xy should be x squared e to the minus y plus y squared. And then that will satisfy both partial derivatives, and I can get both of the components I and j respectively of the vector field. Okay, so now we're going to plug in these 2 points. So I have x and y, and x and y, and order matters, so we're going to do the line integral of f dot dr. In this case should be f of the terminal point, 3, 1, minus f of the initial point, 1, 0, and we're plugging those x and y values into this function here. So we're going to get x is 3, so we get 3 squared times e to the minus 1 plus 1 squared. So that's the first point, minus, now x is 1, 1 squared e to the minus y is 0, plus 0 squared. This is going to equal 9 e to the minus 1 plus 1 minus this whole term, e to the 0 is 1, 1 squared is 1, so this is going to be minus 1, that 0 squared goes away. So we get 9 e to the minus 1 plus 1 minus 1, those two 1's cancel. So the whole thing is 9 e to the minus 1, just some number. So going from point 1, 0 to 3, 1 is going to cost us 9 e to the minus 1 units of whatever we're considering this. Some kind of energy probably. Okay, so that's problem 6. Okay, problem 7, we are going to use work. So we're going to do work done by the force field F in moving an object from A to B. So we're going to say work is the line integral of the vector field xy dotted with dr, but we're going to simplify that to f of b minus f of a. I can only do that if the vector field is conservative. So we can do this if f is conservative. Oops. But the last couple ones we've been working with have been, so that's kind of the theme now. So we'll see how it's going to work. So let's check that conservative vector field. So the I component is 6y to the 3/2 with respect to y, which would be 6 times 3/2 y to the 3/2 minus 1, which is 2/2. And that's going to equal 18 over 2, 9 y to the 1/2, which is the same as 9 square root y. Then we're going to check 9x square root y with respect to x. And that one's real easy. The x just goes away and we get 9 square root y. And these are the same. So f is conservative. I get tired of writing this word at some point. Okay, f is conservative. So now we're going to say partial f with respect to x of xy should have equaled 6y to the 3/2, which implies the original function would have been, there is no x in there, so just add an x. 6xy 3/2 plus g of y. Some function that might have had just y's in it. Partial f with respect to y should have produced 9x square root y, which I'm going to write as y to the 1/2, which implies that we should have f of xy equals the antiderivative of y to, so this is 9x y to the 3/2 over 3/2 plus some g of x potentially, but this is going to equal, this is the same as 9 times 2/3, which would be 18 over 3, which is 6 with an x with a y to the 3/2, and we notice that those two functions are exactly the same. Therefore, I don't need these extra functions of integration that could have popped up because of the nature of partial derivatives, where we let one letter become a constant. So that should be the function. So our function is 6xy to the 3/2. And now we have to plug in our A and B. So A is 1, 1, and B is 2, 4. So we're going to get our work is that, well, let me not write this line integral again because we already showed that it should just be the function evaluated at point B minus the function evaluated at point A. The function at point B, x is 2, y is 4. So we're going to plug that into this function here. X is 2, y is 4, minus the other point is 1, 1. So x is 1, y is 1. This is going to be 12. Now, you can do this in one of two ways. You can take the third, you can take 4 to the third power and then take the square root of that, or what I think is easier, take the 1/2 power of 4, which is the square root of 4 raised to the third. So the square root of 4 is 2 raised to the third. This is going to be 1 to any power is 1, 1 times 1 is 1, so this whole thing is 6. This is going to give us 12 times 8 minus 6. 12 times 8 is 96, minus 6. The work done is 90. Did they give us any units? They did not give us units. So it depends on our measurement and what we're working with here. Like if this was like feet and the force was in pounds, then the work would be foot-pounds. So depends on what unit you're given to interpret what this number really means. But for this problem, problem 7, the work would be 90. Okay, for problem 8, it gives us a vector field and it asks, is the vector field shown in the figure conservative? So, and it says let C be a circle centered at the origin, oriented counterclockwise. So if I have a circle oriented at the origin going counterclockwise, notice that that is going with the vector field F. If it's going with the vector field F, then the field, this motion with the field will be positive. Now for it to be conservative, we need this to equal 0. So because this is a positive, it's going with the vector field, we're going to get a positive result. Because we're going counterclockwise, this is not conservative. So this is going to give us a positive result. And if we would have gone the other way, so let's say we did go, so that one was counterclockwise. Let's say we went clockwise. This is opposing, it's going the opposite of the vector field. That would produce a net negative result. And there is a case where if this curve C is set up so that the partial derivatives, like we saw before, are equal and opposite, then we get 0 and then it is conservative. But this one, based on our description, would not be conservative because it has positive orientation. Okay, the last two problems are on an idea of open, connected, simply connected. So first we want to get a sense of what these curves look like. So this is a circle, so it has x squared plus y squared, which in polar coordinates we know is r squared. And it says y is greater than or equal to 0. Well, we can take a square root of both sides and basically say that the radius of this is 2 circles of radius 4. So we can plot that out. 1, 2, 3, 4. And so now also y bigger than or equal to 0 is going to completely eliminate the lower hemisphere. So we're only going to have a circle from 3 to 3 to 3, half circle, and then the other radius is 4 to 4 to 4, and this will be what we call region D. Okay, now what kind of a curve is this? Well, this is connected. So connected means any line segment that is in D has to be entirely in D. So any point in here is connected to any other point with a simple curve. So for example, I could pick, let me pick a nice color here. Let me go by that. I pick this point here and this point here. Well, there is only one, well, many, but there does exist a curve that is connected from those 2 points. And any 2 points I pick in there, there's a simple smooth curve that connects them. So that would be connected. Simply connected means it has no holes. So simply connected means no holes. So for example, there might have been a situation where inside of D there was a hole, and so we would have written a little hole like that. Well, now that makes this thing a little different, so it's not simply connected anymore. So it's not simply connected, but we didn't have a hole, so we can say it is simply connected. Okay, so, and then open would be like if our curve was just some line segment and it was just open kind of all over the place. It's not a closed, and I should mention too, because this says y is greater than or equal to 0, this is closing this off at the y-axis. So those are end-capped. Okay, so let's look at the next one. The next one says x has to be bigger than 0 and y has to be bigger than equal to 0. So x bigger than 0 means anything to the right of the y-axis would work. Anything over here. And then y being bigger than equal to 0 is this y-axis and above. So when we put these two together, the region D is the entire first quadrant. And so again, this is connected because we have any 2 points we pick in here would be connected by some smooth curve, and it's simply connected because there's no holes. So there's no holes in that region. And this one is technically not open because we could say, okay, I want to eventually cap this off and say this is my region, just that chunk. So we can, it's not like this line up here where it's open over here, it's open over here, and all around it. Okay, so that would be problem 10 and chapter 16, section 3.